Good morning students. Today we are going to discussing about the ideal transformer. My name is P. Mahmud Khan. I am working as an assistant professor in VVT College. Learning objective to learn about ideal transformer on no load condition with the phasor diagram, and we are going to be learning about the efficiency of the transformer also. What is an ideal transformer? The transformer which is free from all types of losses is known as an ideal transformer. It is an imaginary transformer that has no core losses, no ohmic losses, and no leakage flux. The ideal transformer has the following important characteristics. First one, the resistance of the primary and the secondary winding becomes 0, that is R1 equals to 0 and R2 equals to 0. The core of the ideal transformer has a infinite permeability. The infinite permeability means less magnetizing current required for magnetizing their core. Third one is the leakage flux of the transformer becomes 0, that is whole of the flux induces in the core of the transformer links with the primary and the secondary winding. And the fourth one, the ideal transformer has a 100% efficiency, that is transformer is free from hysteresis and eddy current losses, that is we are not having any losses, we are not having any resistance, and flux linkages are going to be total flux is going to be links with the primary and the secondary winding. The above mentioned properties are not possible in the practical transformer. In an ideal transformer, there are no losses. Therefore, the output power is equals to the input power. That is E2I2 equals to E1 I1. Input power equals to your output power. That means from this E2 by E1 equals to I1 by I2. Since E2 directly proportional to your N2. Why? Because we know the equation of your transformer. E2 equals to 4.445 Fn2, and E1 is also directly proportional to your N1. This is also from the transformer equation. And also E1 is similar to your V1. If you neglect the losses, E1 is equals to your V1 and E2 equals to your V2. Therefore, transformation ratio is given by the above below equation. Substitute this value E2 by E1 and V2 by V1, E2 by E1 equals to N2 by N1 equals to I1 by I2 equals to K, transformation ratio. The primary and the secondary currents are inversely proportional to their respective turns. Behavior of an ideal transformer on no load condition. Consider an ideal transformer is shown in figure. This is the figure. We are considering an ideal transformer. The voltage source V1 is applied to the primary winding of the transformer. We are applying a voltage V1 here, and here we are having a N1 number of turns. Their secondary winding is kept open. Here secondary is going to be kept open. The N1 and N2 are nothing but number of turns in the primary and the secondary windings. The magnetizing current in the magnetizing the current IM is the magnetizing current flows through the primary winding of the transformer. Here only this secondary is going to be open, is nothing but the transformer is having only the magnetizing current whose magnitude is IM. This magnetizing current produces a flux. If you are having an alternating voltage, an alternating current is going to be flowing. An alternating current is nothing but an alternating flux is flowing through the core. As the permeability of the core is infinite, the flux of the core links with both the primary and the secondary windings of the transformer. This flux is going to be linking with your primary and your flux links with your primary and the secondary winding of your transformer. The flux links the primary and the primary winding, induces E1 here. When the if you are having a number of turns, automatically here induces EMF E1 because of the self induction. The direction of the induced EMF is opposite to your applied voltage. Is going to be the induced EMF is going to be is equal and opposing according to the Lenz's law. The EMF E2 induced in the secondary winding of the transformer because of your mutual induction. Next, phasor diagram of your ideal transformer on no load condition. The phasor diagram of your ideal transformer is as shown in figure. As the coil of the primary transformer is purely inductive, The magnetizing current induces in the transformer lags 90 degrees by the applied voltage V1. The E1 and E2 are the EMF induced in the primary and the secondary winding of the transformer. The direction of the induced EMF is inversely proportional or opposite to the applied voltage. First, because of the current, when current is going to be flowing, then only what happens, we are getting the flux. That means if current increases, flux is also going to be increased. These two are going to be in phase. We are taking I as a reference one and the flux as this one. Automatically what happens and from the EMF equation of a transformer, phi equals to phi m sin omega t, automatically what happens, the self-induced EMF which lags 90 degrees by your flux, therefore we are getting this as an E1. This is the phi direction, this is nothing but your E1 direction, and we are getting the E1. But E1, what happens, E1 exactly 180 degrees, which is going to be opposite in nature. 180 degrees phase shift with your V1. This is the phasor diagram of your ideal transformer no load condition. Points to be remembered: the input energy of the transformer is equals to your output energy. The power loss in the transformer, ideal transformer, becomes a zero. That means no losses are going to be existing. Next one, efficiency of the transformer. What is an efficiency? The efficiency of a transformer at any load power factor is defined as the ratio of output power to the input power. Efficiency is nothing but your output power to the input power. Therefore, output power divided by input power, we can able to write as input power equals to output plus losses. We are applying the input. Whenever you are applying the input, we are having the output. Some losses are also going to be existing. Therefore, output plus losses. What are the losses? We are having the iron losses and the copper losses, and therefore therefore we can able to write output power in the transformer kVA cos of phi. Output power, this is nothing but your transformer rating, and cos phi is nothing but the power factor. Output, this is nothing but your output. Therefore, output by plus losses, that losses is nothing but your iron losses plus your copper losses. Wi stands for iron, and Wc is nothing but your copper losses, into 100 is nothing but percentage efficiency. If you wanted percentage efficiency, if you are multiplying with the 100, where cos phi is nothing but the load power factor. Load power factor is nothing but cos phi r by z. We already discussed the angle between your V and I, it is called as a power factor, or r by z. We can able to write it as an P by P by S also. And W is nothing but your iron losses, Cu is nothing but your copper losses, Kv is nothing but the rating of your transformer. There are no moving parts or rotating parts in the transformer. That is, we are not having mechanical losses in a transformer. Therefore, we are not having any mechanical losses in it. Compared to the machines, transformer will have a high efficiency. So, transformer efficiency is much higher than any other rotating part. This is the feedback from thanking you.